Okay, guys, so thank you for waiting. As you all know, everybody's speaking about DevOps, everybody's building pipelines, but we need to think about performance from time to time. So Ionut is here to share his experience with us.
Okay, thank you very much for this introduction, and thanks all to coming. We are going to discuss about architecting for performance. It's not quite related to DevOps, but I think it's quite a keen topic for you. So thanks to all for coming. My name is Balosin. I'm currently software architect for Luxoft. Apart software architecture staff, I'm technical trainer. I'm particularly interested in areas like performance and tuning and software architecture. You can find my courses on luxoft-trainings.com. Speaker to conferences, and from time to time I write technical articles. So what is our agenda for today? We'll discuss about a bunch of design principles from the performance architecting perspective. We'll continue with some patterns, data structures, algorithms, all of them which might go hand in hand with performance. We'll continue with OS guidelines, and we'll end up with some hardware guidelines. In terms of abstractions, the first layer, the design principles, has, for example, bigger abstractions, which is in opposite with the complexity. Since we go down to the hardware, the complexity is increased more and more. What's mainly the target audience for today? The topic is addressed to the performance engineers, software architects. Why? Because in the projects, when you design your architecture, you sometimes need to face the performance as a quality attribute. So that's why we will share today a lot of tools, tips and tricks useful for you to architect for the performance. Not only for these two, also for the developers interested in the performance topic and everybody else. So first, what is the performance? How you would define the performance? The performance is very simple to be defined. It's just to satisfy some time requirements. That's it. If you don't have these time requirements, your quality attribute, the performance, is not an important one. So here I wrote an article for the InfoQ. It's quite recent, where I explain a bunch of, let's say, leaky terminologies we are using in IT industry. Across these terminologies are so-called non-functional requirements. So in this article, I explain why it's not appropriate to use non-functional requirements for your applications, because performance, scalability, as a group, all the elities are not quite non-functional requirement. My advice for you is to stick with quality attributes. By books, from software architecture perspective, they are called quality attributes. That's all being said, let's kick off with design principle. What would be the design principle useful in context of performance? First of all, it's about the abstractions. As Dijkstra said, the purpose of abstractions is not to be vague, but on the contrary, to be more and more precise. And the question that arises, how abstractions impact performance? For example, in Java, in C++, in C#, all abstractions are mainly implemented via polymorphism or virtual calls. The thing is that during the runtime, the virtual calls are costly. Why? Because in particular in Java, the virtual calls are resolved via the vtable lookup. So every time you have a virtual call, a vtable lookup, it's invoked to get the actual target implementation. So it decreases the performance and increases the response time during the runtime. My advice for you is to be conscious when you use abstractions and to minimize the number of abstractions in your application. The next one is called Cyclomatic Complexity. It's mainly about the independent paths that you might have during the runtime. For example, in this case, you have a bunch of if-else scenarios. You end up with a higher cyclomatic complexity. The thing is that the CPU, there are some CPU predictors. They are natively implemented in the CPU. So if you have a higher cyclomatic complexity in your application, you mess up the hardware predictors. So during the runtime, you have to wait and you will end up with a lot of CPU stalls. The period of time of inactivity from your CPU, if the cyclomatic complexity is higher, because it's also more difficult for the CPU to guess and to anticipate what you are going to do next. Also from the testability standpoint, cyclomatic complexity is bad not only for the performance. The next one is called algorithmic complexity. We learn from high school, from faculty, all the time we learn about bigger complexity. The thing is that lower the bigger complexity is, your algorithm, your response time, it's slower. And it's good. Our purpose is to increase the serviceability or the service time. It's all about the magnitude of n. But the question that may arise is, how important is bigger complexity? I mean, is it accurate enough to stick only with the bigger complexity? Probably no, probably yes. Today, I took an example, very, very basic one, about the matrix multiplication. The classical example, it's the one that we already know, familiar with. And I tried to compare the classical implementation with the Strassen algorithm, which is, by theory at least, a small improvement in terms of the performance over the classical one. What does the classical one? It has mainly 3 loops. I call it AJK because the first loop is the second one is J, the third one is K. So I call it classical AJK algorithm. And if I have to represent the visual for it, how it works, the matrix, the first matrix, it's traversed by line. So it's a predictable pattern. It's like you traverse an array from element to element. And the B matrix is traversed by column. And here you have the result. What happens, the complexity, it's cubic, it's n of power 3. What happens, because I'm not very convinced about the performance of this algorithm, I searched on the internet and I found the Strassen algorithm, which is supposed to work better only in certain conditions. For example, if the matrix size is more than 100 elements, the Strassen algorithms might be an improvement for that. And at least by theory, the complexity for it, it's n of power of 2.80 something. I create some very sample programs and I tested for different matrix size, for example, 520, 2K, and 8K elements. And in case of classical one, I've got a bigger number of seconds per operation. The lower it's better in this table. So the Strassen one beaten the classical algorithm. And the next question that arises in my head is, can I improve in a way the classical algorithm, IJK algorithm, to be better than the Strassen, but keeping the same complexity? It's not a trivial question. You shouldn't find that answer without profiling the hardware. If you profile the hardware, in particular the CPU, you will see that the matrix B, it's very non-CPU friendly because you traverse the elements by column. So that's why, in a way, if I can slightly change the classical implementation to be more CPU friendly, to be more predictable during the runtime, probably in that context, the classical one will beat the Strassen algorithm. And this is what I did mainly, because this loop caused a lot of misses. So the CPU during the runtime had a lot of CPU stalls, periods of inactivity. I decided to just replace these 2 loops and to be more predictable, but again, keeping the same complexity, because from theoretical standpoint, I still have 3 inner loops. So the complexity is still cubic. And in this case, I test it again, and the Strassen algorithm on the left side was beaten by the classical algorithm. which leads me to the conclusion that it's not always about the bigger complexity, but you need to understand the hardware and you need to understand the memory access patterns, because otherwise you won't squeeze the ultimate performance out of your application. The next category, it's about the patterns. So we will discuss about the patterns, how we should be more predictable when you access your data structures and things like that. Patterns, in this world of accessing memory, there are around three ways. You will find more, but it's about three. The first one is sequential. Being sequential, it's exactly like being predictable. For example, let's suppose this is my entire heap, and I walk through the page using a predictable pattern. This is very CPU friendly because the CPU prefetcher can guess my next execution and add the element in advance for me. So I don't have to wait when the next execution is effectively executed. The second one, it's called spatial, which refers to the fact that, for example, I have a bigger chance to request elements collocated to that one that I used before. It's about the spatial, as you can see in here. And the third one, it's temporal, or you can think about it as a randomly walking through the entire heap and access elements, and there is a bigger possibility to request again an element that I requested previously. I did these 3 test cases in a Java simple application, and I've got this response time. For the sequential pattern, I've got about 1 nanosecond per operation, which leads me to the conclusion that it's incredibly fast. Do you have an idea what's the latency to retrieve something from the L1 CPU cache level? It's 1, 2, or 3 nanoseconds. So it leads me to the conclusion that in case of sequential, there is almost no latency. Everything is in L1 CPU cache level. The second way, it's called spatial. It's not so predictable, but still in this case, I've got around 5 nanoseconds per operation. In this case, it might be taking into account the second level of the cache. Still, there weren't too many CPU stalls, so the latency was very, very small. And the third one, in case of temporal, it was about 40 nanoseconds. Still, it's good, because, for example, if you want to retrieve something from the main memory, it's around 100 nanoseconds. Just to request your object from the main memory and to put it in your cache. So in this case, it leads me to the idea that in case of temporal access through my heap, I've got chances for my objects to be stored into the L3 level of the cache, which is still good. But again, think about memory access patterns because they count a lot. For example, think about the array versus linked list, all these kind of things. More predictable you are and less dependency, data dependency you have, you will help your CPU and your application will be more performant during the runtime. In case of data structures, I'll share with you a hash map from 2 ways, the chaining implementation and the open addressing implementation. Java doesn't have by default in the JDK the open addressing. There are some third-party libraries that are using open addressing. C# has one. I think C++ in the Boost library, there is also an implementation for the open addressing. So default one in JDK is the chaining. It's simple as that. So what we have here, we have our buckets, we have an array, we have buckets, and inside each bucket there is a pointer to a linked list, and you put the elements in that linked list. In our case, if we add, for example, this element, which is defined by a hash code, it was placed in here in this bucket, and there is a pointer to the linked list which contains just one element. After a few cycles, I added another one by DDD hash code, so there is no collision. It was added into another bucket, which was fine. And in here, you can see the memory layout. So the memory layout, because it's a linked list, could be up to the OS allocator. So you do not have any guarantee that the objects will be collocated in the memory. But what happens in case you have collisions? Let's suppose your application ran for a certain amount of time and you have collisions. In case you have collisions, and you add another key in here, you add another element having the same key, and you have collisions, it's about chaining. So you edit another element in this linked list, and the memory layout could be very, very spread. I mean, the objects are not laid out in the memory. That's an issue, because when you have to retrieve those objects again from the main memory, you have a temporal memory access pattern because the objects are not collocated. In Java, for example, for a full GC cycle, especially the ones that does compaction, there is a better chance for these objects to be collocated again, but you have to wait for the next full GC cycle until your heap is defragmented. In comparison, the open addressing scheme, as I said, it's not by default in the JDK. The open addressing do not use the chaining. There is just the array itself. What happens if you add an entity in here by hash code AA, it is just stored in the array itself. If you have to add another one after a few cycles or later on by different hash code, it is placed in the array itself. And as you can see, the memory layout in this case, it's predictable because it's an array. And what happens in terms of collisions, how the collisions are handled by the open addressing? If there is a collision, there are some ways. There are some probing algorithms. And in this case, I use the probing, the linear probing one, which happens, what means, for example, in case I have a collision, and here I have another element, because I'm using linear probing of interval 1, I search inside the array list one by one, and I found the next available slot. And the element is added in there. This way, the memory layout, it's very, very compacted. So in this case, we benefit of the sequential memory access, because it's mainly like an array stored in the memory. If I have to compare this chaining and open addressing, there are pros and cons, of course. For example, the memory, it's bigger in case of chaining because you have a lot of pointers in between the objects. On the other side, the open addressing, it's shorter, it's just an array. The drawback of open addressing is, for example, if your number of objects is closer to the load factor of that hash map, you might, for example, face a performance penalty. Why? Because the open addressing scheme scales better until the number of elements is less than the load factor of that hash map. Otherwise, you'll find out some performance penalty. Open addressing, it's always something you have to keep in mind and you should tackle if you deal with hash maps, and in some particular cases there might be a good choice for you to use it. As Martin Fowler said, the choice of data structures always counts. Make a big difference across the developers. By practice, a lot of performance issues in the applications, not a lot, but the majority of them are coming from improper or misuse of data structures. It's very important for you to understand the basics. For example, the the art of computing programming volumes, it's handy to know the basics. There are algorithms and data structures written several decades ago, but they are still valid. We tend to go into more abstractization, adding layers over layers by different frameworks, but we don't know the ground through the basics, what really makes a difference. If you want to program from a performance standpoint, one very handy tactic is to use log-fig programming. What's log-fig programming? The log-fig programming guarantees there is an overall progress inside your application. For example, imagine you have multiple threads. These threads are using some shared memory. And using lock-free technique, there is no such possibility that one thread can lock indefinitely the other thread. Like in the normal programming using locks, it might happen because the locks are not reliable. There are some issues called priority inversion. Locks are preemptive. All these kind of issues associated with the locks disappear in case of lock-free programming. And one tactic to use lock-free programming is to stick with the compare and swap instruction. It's an atomic instruction which says that I can atomically update, for example, the value from the main memory if I have the last value of read written from the memory. In this case, for example, suppose we have two threads. The first thread, which has the last value read from the memory of 99, which corresponds to the 99, and another thread which has another value, 98, which is stale, it's outdated. If each of these threads tries to update the memory, the first one will succeed and the second one will fail. What could happen in this case? Of course, the second one could try to read it again and try to update it later. It's very similar with the optimistic locking perspective. How it is implemented in the hardware, it's mainly this atomic instruction compare exchange. The thing is that it is atomically. In Java world, we have some APIs, for example, the Java util concurrent atomic package, compare and set. So by default, it uses the atomic instruction and some other structures or APIs which are using under the hood compare and swap. Like, for example, get and increment, get and decrement, reentrant locks from Java are using compare and set. Concurrent link queue, it's a very performant queue implementation which doesn't use the real locks. It's based on compare and swap. So be careful with these structures, because if you design in a high performance field, there might be your first option when you write the code. The third level, it's for the OS guidelines. In terms of OS guidelines, thread affinity is always an option for you. What says the thread affinity? It's mainly to bound my thread in the application towards one core or several cores. In the modern architecture, hardware architectures, you have multiple sockets, like in here, inside each socket. On each socket, there are multiple cores, and each core could have like 2 virtual threads, because it's hyper-threading. The thing is that if my thread is scheduled against this core, and after a while it is rescheduled by the OS, it might be scheduled on another socket, another core. This is not very performance friendly, because you'll invalidate all the cache levels. So invalidating all the cache levels, I'm referring to the CPU cache levels. Once you reschedule the thread on another core, you have, at least for the first iteration, first cycles, to wait. The CPU will stall to repopulate the cache. In this context, if you can bound the thread to one or two particular cores, you'll benefit of the L1, L2, and or L3 cache CPU levels. So you'll be more predictable, more performant. In Java, unfortunately, there's not a big support for this, and it makes sense because it's kind of abstraction language. But nevertheless, there is a Chronicle thread affinity library, which is handy. And in Linux, there is a task set command. In C, C++, it comes very handy because it's a native language, so you have the APIs in there, so it's more useful. But in Java, it's quite limited, this thread affinity. Non-uniform memory access, it's another, let's say, design you should care of when you deal with high-performance systems. What happens in modern architectures, as I was mentioning, there are multiple sockets, and each socket has sort of local memory. This is called NUMA Node 1 and NUMA Node 2. What stands non-uniform memory access? It refers to the time I can retrieve an object if my object it's relative to my local CPU. For example, if I have a thread schedule in here, and on that thread I want to request an object which is not in this RAM, I have to request it from here. what would happen? I have to stall until my object from here reaches the cache line in here. So I have to wait for the hypertransport and QPI to retrieve my object. Hypertransport, it's in case of AMD, and QPI, Quick Path Interconnect, it's in case of Intel. So I have to pay all of these CPU stalls. It's better when you allocate something to be allocated locally to your local socket, because you don't have to wait until it is retrieved from the remote memory. Java offer a bit of support. I'm saying a bit of support. The hotspot implementation or OpenJDK implementation offer a bit of support on this. Why? Because this is valid only for the parallel GC. If you are not using the parallel GC, but other collectors, non-uniform memory access, it's not quite an option for you in Java. As Oracle said, the NUMA performance metrics, if you activate the NUMA, in some cases, just by adding a JVM argument, you can benefit around 30–40% of your speed during the runtime. That's it, just to say, I want to start my JVM with NUMA activated. In Linux, there is a NUMA command line. It's called NUMA control, which can, for example, if you start the process, you can bound that process to some, you can control maybe what's in here, bound that to the socket. Large pages, it's another handy optimization. What happens when you, for example, translate a virtual address to a physical one? First thing which happens is that a TLB, it's inspected. The TLB stores the latest transitions, the latest virtual to physical memory translations. If there is a TLB hit, which means the virtual memory wasn't recently used and stored in the TLB, we have a miss and a page walk happening. The thing is that the page walk is very costly. In order to minimize the page walks, there are two options mainly. To make the TLB bigger, which is not a case. Why is not a case? Because the TLB should be very, very fast. If you have the TLB bigger and bigger, you will still pay the latency to inspect the TLB, or make the pages bigger. The pages by default are of 4Ks. You can make them on, for example, as in here, 2 megabytes, 1 gig, 2 gigs. Depending on your application, you can enable large pages. This is a command line from Java and explicit the size for that pages. You can as well enable transparent huge pages, which is slightly different than large pages, but it's mainly the same idea. Nevertheless, in all these cases, you have to enable DOS support. To enable DOS support on Solaris, it's by default. In Linux and Windows, there is the huge pages are not enabled by default. And in case you deal with a lot of I/O reads and writes, it's always better to use RAMFS or TempFS. Why? Because, for example, in my tests, RAMFS, comparing to HDD or SDD, it's around 10 times faster. It's always better to write and read from the main memory instead of reading from the physical disk. So that might be another option for you. And the last part, it's about the hardware guidelines. And in here, the fault sharing, the first one, it's all the people talks about the fault sharing. What is fault sharing about? Imagine you have an instance which has 2 fields, and you have 2 threads. Each thread updates different fields. On theory, you don't have contention because each thread updates its different field. But in practice, there is a contention on the hardware level. Why? Especially in the case where all, those 2 threads are scheduled on different cores. Why? Because, for example, if my object it's on the 3rd cache line, you will have here X and Y, and each thread updates X, the other thread updates Y, and there is a synchronization in here on the 3rd cache line because X and Y are on the same cache line in the CPU. It's better to split X and Y to not be on the same CPU cache line because you don't have any more contention on that cache line. So even in this case, in theory, there is no contention at the program level, and in hardware there is contention in the CPU line. Java added the contented annotation for this, which mainly splits X and Y and puts both of them on different CPU cache lines. So in this case, as we can see here, the throughput was around 4 times bigger than the baseline. The baseline is where you don't use any padding, any contented annotation, anything, because there are a lot of options. And she states it's finally the last advice for you to think of. What happens natively in hardware, for example, if one CPU has less activity, it might switch the state from 0, the 0 is the state of full activity, to 6. In 6, your CPU, the clock cycles are cut and you save the energy. That's the idea around C states. So if there is an inactivity on your CPU, the signal is clocked and you save the energy. The thing is that when the OS schedules something on that CPU, it requires more time to reach a steady state. So you will suffer of the performance during the runtime. That's why maybe it will be another option for you to disable the C states during the runtime. You will pay more for the energy, but you will be more predictable and your CPU will be in a steady state for all the life cycle. I really like the code from Sergey Kusenko, which is a performance engineer from Oracle, which said that profiling is simple, or you have to know it's everything. I would say, profiling. I would say performance is simple, all you have to know it's everything, as you saw in this talk. Thank you very much.